Well, welcome back. Now we're in starting section 2.8, linear approximations and differentials. Now, this is one of those notation things, but they actually have some meaning to them. Now, we all know from a long time ago, algebra, pre-algebra class and stuff, and the slope is y2 minus y1 over x2 minus x1, rise over run, all the formulas, but it's also known as the change in y over the change in x. And we know the derivative, you've been programmed, that the derivative is going to the slope of the tangent line, and we use the Leibniz notation dy dx for obvious reasons. So when you put these two guys together, because this is a special type of slope of the tangent line, that the delta y over delta x, change in y over change in x, is approximately dy over dx. This will be the slope of the tangent line at that particular point. We also know from our notation, from like next to Newton's notation here, Newtonian notation, that dy dx is equal to f prime of x, f prime the standard derivative. But so we created this formula for you as dy over dx, also known as derivative, is equal to the derivative f prime of x. You can manipulate this from algebra and actually solve for the dy dx. If we solve for the dy, and so if I solve for dy in terms of dx here, dy over dx equals f prime of x. So if I multiply by dx on both sides, I get this equation. Dy is equal to f prime of x dx. And this notation right here is what we call the differential. So first thing, the concept of differential is a formula, straight up formula. It's dy equals the derivative of your function times dx. Now be careful on this because sometimes they'll change the notation, like I have volume equals 4/3 pi r cubed or something or other. Well, then the variable of the dependent variable would be v and the independent variable would be r. So you can switch up these letters and stuff, but standard notation is the differential is dy equals the derivative with respect to x times dx. So first problem here is this. Find the differential of y given that y equals 5x cubed times the sine of x. Well, they want me to find the differential. Here's my formula for the differential. So here we go. Dy is equal to the derivative times dx. This is the notation. What I need to do is take the derivative of this guy. So in my notation here, this tells me that dy would be the derivative. Now, how would you take the derivative of y equals 5x cubed times sine of x? With that big old times in the middle of it, again, this is going to be the product rule. Product rule, derivative of the first times the second plus the first times derivative of the second. So you'll notice throughout these sections, we're still trying to reinforce all these derivative rules. So the product rule, derivative of the first, that would be 15x squared, derivative of the first times the second, sine of x, plus the first, 5x cubed times derivative of the second. And derivative of sine of x is cosine of x. And so there is my derivative, but the notation for the differential is dy equals the derivative of your function, and you write them out, times dx. And notice these brackets around this thing, times dx. That is the differential notation. So here's another one. Try this one. Find the differential of f of x equals the square root of 5x squared plus 2x minus 12. All right, well, once again, I have my derivative of f of x, and typically f of x is the same thing as y in our standard college algebra pre-calculus notation here. So I'm going to use my same notation. Dy is equal to the derivative of my function, dx. And now, so dy would be equal to, and now I need to take rid of this guy. We'll take rid of this guy. What rule would we use? Well, first off, I don't do square roots. Square roots is a half a power, so this is 5x squared plus 2x minus 12 to the half a power. And to take rid of this guy, I'm going to use a chain rule. 1/2 pops out front. The inside, 5x squared plus 2x minus 12 stays the same. Raised to, subtract 1, raised to the negative 1/2. Times the derivative of the inside. The derivative of the inside is 10x plus 2. So chain rule, derivative of the outside, inside stays the same time derivative of the inside. So the 1/2 pops out front, the inside stays the same, raised to the negative 1/2 times derivative of the inside. But they didn't want the derivative, they wanted the differential. So the differential is dy equals the derivative of your function, which is what we got here, and then times dx in the back. But be careful. Let me just give you an extra little side problem here. And that would be something like this. Let's say, for example, so I'm going to actually use a little side point over here. Let's say I gave you volume equals 4/3 pi r cubed. Just to be familiar with this notation. Now, there's no y's in this thing. There's no x's in this thing. So if I wanted the differential, I got to use the variables that are given to me. The dependent variable is volume, v, and the independent variable is r for radius. So in this notation, because I'm dealing with v's and r's, the differential would be dv equals, bracket, the derivative of your volume function, but then times dr, the independent variable. That's the pattern for this thing. So the differential of the formula volume equals 4/3 pi r cubed would be dv would be the derivative. Well, the derivative of 4/3 pi r cubed, well, 4/3 pi is a constant that holds over. Derivative of r cubed is 3r squared. But then you got to do times the independent variable, dr. Of course, you always want to clean this stuff up so the 3's cancel, so you're left with dv equals 4 pi r squared times dr. That would be the differential of this particular equation. Okay? So pay attention to your variables, but the standard notation is the old y's and x's, so your differential is dy equals the derivative of your function dx. So that being said, what's the point of all this stuff? All right, well, the point of all this stuff is what exactly differentials do. So your professor is going to go into great detail about the purpose of what's going on here. We're going from slopes of secant lines down to slopes of tangent lines. So if we actually talk about 2 points, x and what we call x plus delta x plus a little bit, if we plot them in some kind of function, here is x, so this would be the f of x, y coordinate. Here's x plus delta x, so when I plot him, he's right here. This is f of x plus delta x. And our notation is, if we wanted the delta y, or change in y, that's f of x plus delta x minus f of x. It's the difference between the two, and that's what we wrote for you here. And delta x is the change in the x's. That's x plus delta x minus the x, which gives you the delta x. So delta x is the change in x's, delta y is the change in y's. So from our notation of derivative and your slope being change in y over change in x, we come up with this. Delta x is approximately dx, delta y is approximately dy, and from formulas, the dx is the same, approximately delta x, but the dy is approximately delta y, which is that f of x plus delta x minus f of x. So what the differential is actually helping us calculate is the change in the y coordinates. It's approximating the change in y coordinates. So let's take a look at this example. Area equals pi r squared, area of a circle. Use differentials, pay attention to directions. Use differentials to approximate the change in area from going from r, radius of 4 feet, to a radius of 4.2 feet. All right, so differentials, it says use differentials. So the differential formula, dA would be the derivative of your area formula times your independent variable. My independent variable on that would be r. So this is my formula for the differential of this formula. Area equals pi r squared. Area is the dependent variable, r is the independent variable. So it's dA equals the derivative of your area equation times d independent variable dr. So now I need to take derivative of this guy with respect to r. So dA would be, well, derivative of pi r squared, pi is a constant, bring down your power, that would be just 2 pi r times dr. This is your differential. So now, your r is fixed at 4 feet. What would the change in r be if I'm going from 4 to 4.2? Well, to calculate the change in r, that is the end minus the beginning, or in other words, 4.2 feet minus 4 feet, which is equal to 0.2 feet. That's your change in R. And remember, dr is approximately delta R, which is equal to 0.2 feet. So I'm going to plug all that information in here, and I get my differential being equal to 2 pi R, and R was 4, times dr, and dr is 0.2. So it's a literal plug and chug here once you get this information. So let's clean this up here. So I got 2 times 4, which is 8, times 0.2, which is 1.6. So for you math fans out there, dA would be 1.6 pi. And if you wanted units on this stuff, and if you're in my class or some of the other professors, we're going to really stress the concept of units. This is the differential, which approximates the change in your function. My function is area. So the change in my area going from 4 to 4.2 feet is approximately 1.6 pi. And it's area, so that would be your units feet squared. And for those fans of figuring out from the decimal perspective and wanting to actually see this thing, also we would accept dA for web work purposes is 5.026548246 feet squared. Now remember, on web work, don't put your units. But on word problems, definitely put your units if you're turning it in. So, in other words, if I've got a circle and I went from a radius of 4 feet to a radius of 4.2 feet, so it expanded, got bigger, that would have an approximate change in area from going from 4 to 4.2 feet of 5.026 feet squared. That's how much extra area approximately you would have. This is what the differential does for you. But now, just to compare, I want to see how good this stuff is. Now, find the actual change in area. To find the actual change in area, this would be dA, delta area. That would be the area at end, and when the radius was 4.2, minus the area when the radius was 4. This gives you the actual change in area. Now if I did this right, the answer I'm going to get down here should approximate this guy here. So the change in area, delta area, would be the area, which is pi r squared, pi, and my radius would be at the ending point at 4.2 squared, minus your area, which is pi r squared, but now their area was 4 squared. So your delta area would be equal to, and I'm going to show you that this really becomes calculator work now, so I'm going to throw my calculator up here. And I brought one of my old calculators today. This would be pi times 4.2 squared minus pi times 4 squared. So I'm just literally typing exactly what I see it on my calculator, and what do you get? I got 5.15, and I'll write out all my little decimals here. This is 5.15221195 feet squared. This is the actual change in area, and this was my approximate using my differential. You'll notice that it's a little off, but they're close, and that's the whole purpose. This was close, and I really didn't even need a calculator until I wanted a decimal version of the answer. This one I had to have a calculator right from the get-go, and there's the real difference between the two. And if approximate's good enough, your differential is really going to help you out. But again, your professor will go into great detail about these concepts of differentials and the applications thereof. Well, in section 2.8, there's one other little aspect that we want to look at, and that is linearization. Now, this is the end of chapter 2 here, but with linearization, it's a formula. Now, definition. The linearization of a function f of x at a fixed point a is given by the formula L of x is equal to f of a plus f prime of a times x minus a. Now, if you look real hard at this formula, what this formula really is the equation of the tangent line. It's actually using the point slope formula. Because remember, we're talking about linearization equation of a tangent line here. The slope of a tangent line is the derivative evaluated at your point A, so that's f prime of A. Anytime you want to find the equation, we use the point slope formula. Y minus y naught equals m tangent times x minus x naught. So if we plug in the point A, the y coordinate's f of A, so that'll be y minus the y coordinate f of A equals the derivative f prime of A times x minus A. And when you clean this up and add f of A to both sides, you get the linearization formula. The linearization formula is the same thing as the equation of the tangent line. It's a special little form they wrote it out, but it's, if you get in trouble, remember it's the equation of the tangent line. But they're being fancy about it. But when we get you guys into Calculus 2, we're going to expand this concept into Taylor series and Maclaurin series, and actually talk more about how these derivatives play a part in the function and stuff. But this is the beginning, called linearization, equation of the tangent line. So here we go. Find the linearization for the function f of x equals the square root of x squared plus 3 at a equals 2. All right. So let me slide it up so we can see this thing. Well, the nice thing about linearization is if you got that formula memorized, you don't have to do all that point slope formula stuff. So just memorize it. L of x is equal to f of a plus f prime of a, that's a prime there, times x minus a. A is equal to 2. But you've got to have two things. You've got to have f of a and f prime of a. Well, we got f of x. We've got the function, which is the square root of x squared plus 3. Let's find f of a. F of 2 would be the square root of 2 squared plus 3. Let's see here. 2 squared is 4, plus 3 is 7. So that would be the square root of 7. Now we need to find f prime of a. F prime, that would mean the derivative. But if I want to take derivative of f of x, I don't do square roots. Square root's a half a power. So x squared plus 3 raised to the half a power. Now if I'm taking derivative of x squared plus 3 to the half a power, what rule am I going to use? You got it, inside outside chain rule. Derivative of the outside, 1/2 pops out front. The inside, x squared plus 3 stays the same. Don't forget, subtract 1 from your exponent, raised to the negative 1/2. 1/2 minus 1 is negative half. But then times the derivative of the inside, which is 2x. You'll notice that this 2 and that 2 cancel. If you clean this guy up, which may be easier because we're going to plug in numbers into this thing, we're going to get this. We're going to get x divided by, because the negative exponent puts it on the bottom, and a half a power is a square root, divided by the square root of x squared plus 3. So there's my derivative. But that's not the guy we wanted. We wanted f prime of my fixed point A, which is at 2. So this would be 2 over the square root of 2 squared plus 3, which is equal to 2 divided by the square root of 7. Now you can rationalize that if you want to, but this is calculus. We're interested in just getting the answers. So here we go. Now for our linearization equation, L of x is equal to f of a. F of a was 2, so that would be the square root of 7, plus the derivative, 2 divided by the square root of 7, times x minus a, and a was 2. So there's my equation. Now you're right, you can probably go turn these into some decimals, and I probably wouldn't be very nice, but the fact is this is my linearization equation. And usually what we do with linearization equation is to approximate my function at any points near 2. So I would say, what would f, using your linearization equation, what's approximately f of 2.1 going to be equal to? So I would plug 2.1 into my linearization equation instead of my real equation. All right, now that being said, take a look at this next one. That concept about using it to approximate is exactly what you do with this last concept here. Use linearization techniques to approximate the square root of 25.1. So, first thing you got to do here is you got to figure out what your function is. What are you actually playing around with? We're playing around with square roots. So in this problem, f of x would be the square root of x. You will first have to, when you're trying to do a linear approximation of something or other, the first thing you got to do is got to come up with the function somehow. And you need to find a. A is what I call a good point. The good point that's near the point we're plugging in that I actually can do some functions with. So in this case, I'm doing a square root. I'm talking about trying to approximate square root of 25.1. So my A would be a good point that's close to 25.1 that I actually can take the square root of. You got it. A is going to be 25. Now, what you want to do, here's my function, here's my A. We're going to do exactly what we did up here. We're going to find the linearization equation of this guy. So L of x would be equal to f of A plus f prime of A times x minus A. Memorizing our formula here. So I have, I'm going to draw my little line down here so we don't get confused. F of x is the square root of x. So f of 25 is the square root of 25, which is equal to 5. Now I need to find f prime of x. Well, remember I don't do square roots, so that's x to the half a power. So the derivative would be 1/2 x to the negative 1/2. And I'm going to clean them up. This would be 1 over 2 times the square root of x. Remember, negative exponents go on the bottom, and a half a power is a square root. So that'd be a square root on the bottom. So it's 1 over 2 square root of x. So, but we need f prime of my A point, my good point, 25. This would be 1 over 2 times the square root of 25. Well, square root of 25 is 5 times 2 is 10, so this will be 1/10. So here we go. Plugging all this information into my linearization equation. My linearization equation for the square root of x would be L of x equals f of A, which was f of A. A is 25, so f of 25 is 5. Plus the derivative at A, derivative at 25 was 1/10, times x minus A, and A in this problem was my good point, 25. So this is my linearization equation. Now what's the point of this? Now, we want to approximate the square root of 25.1. So I'm going to approximate it by plugging into my linearization equation the number we're plugging in for x, which is 25.1. So what is the linearization of 25.1 in my equation? We'll plug it in. This is 5 plus 1/10 times 25.1 minus 25. This would be equal to 5 plus 1/10, and 25.1 minus 25 is 0.1. And so what is 1/10? 1/10 is the same thing as 0.1. And so when I clean this up, just again for your benefit, 5 plus 1/10 is the same thing as 0.1 times 0.1. Now order of operation, what is 0.1 times 0.1? Well, 1 times 1 is 1, but I got 2 decimals here, so I've moved my decimal place another place over, so that's going to be equal to 5 plus 0.1 times 0.1 is 0.01, and so I'm getting the answer 5.01. So in other words, the square root of 25.1 is approximately 5.01 is what we're saying by using my linearization equation. But I want you to see, I never actually used a calculator on this problem. I did all this kind of calculations in my head. I understand the power of these linearization. It gives you good approximations. Now let's see what my calculator says about this. So if I do my calculator, now this will give you a much closer answer here. But this was just linearization here. But I want to take the square root of 25.1. And what does my calculator give me? Let me put it in the light here, you guys can see it better. 5.00999,002. So, yeah, it's a pretty good approximation, and I didn't need a calculator to actually get the answer. That's one of the purposes of this stuff. There's other examples and stuff. Again, your professor is going to go into great detail of the differentials as well as these linearization techniques, and they're going to have some future applications as well when we get you guys into calculus 2 and stuff. Again, I hope this has been helpful, and I'll see you on the next video.